purpose of this lesson is really going to be problem solving using Newton's laws of motion and using Newton's laws to solve different types of questions that we might see. Basic steps each time when we go to solve Newton's laws are as follows. Draw a free body diagram. Use your net force in the x direction and y force in the y net force in the y direction using Newton's second law. And then we can very simply use trigonometry to solve for our unknowns. Be mindful of the direction in which the object is moving. Because sometimes in those cases, we don't want to do extra calculations that aren't really necessarily needed. So the point of this lesson really is just lots of examples. And here's the first one that we have. A gymnast hanging onto two separate rings that is attached to the ceiling by ropes. And that person is hanging motionless. There's our keyword there in this question. And each angle is 45 degrees. We are going to determine the tension in each rope, and we have a mass of 80 kilograms. So to begin, free body diagram. Let me first say this. We are going to have up and the direction to the right as positive. We have our gymnast who is 80 kilograms in mass with two ropes, each at an angle of 85 degrees. Sorry, that should say 85. With the force of gravity acting down on the gymnast, and remember that's always mass times gravity. From this diagram, let us also label, let's call it a second force acting to the right and a first force acting to the left. So we have these things given to us. Our mass of 80 kilograms, gravity is 9.81 meters per second squared, theta is 85 degrees, and we know because our person, in this case the gymnast, is motionless, that its net force is 0 newtons, and let us calculate our tensional force. So we've drawn our free body diagram. Now let's solve F net in the x direction and in the y direction. I always like to set up my questions in a nice little table. It allows us to easily visualize and plan our course of action. Looking back at my diagram, I can see that I have F1 at x acting in the negative direction. And we know from displacement problems that F1 at x can be calculated by taking the magnitude of force 1 cosine 85 degrees, and that will be negative. Similarly, in the positive direction, we have F2 in the x direction. And F2 in the x direction will be F2 cosine of 85 degrees. And remember that F2 and F1 make up our tensional force. So if I think about my net force in the x direction, which will be the sum of the two, so that will give us F2 cos 85 degrees minus F1 cos 85 degrees, and that is equal to 0. That tells me, therefore, that F2 cos 85 is equal to F1 cos 85, which tells me after canceling out that F2 is in fact equal to F1. And remember that both of these make up our tensional force. Cool. What does this give us? Well, let's look in the y direction. Y direction, similarly, I have F1 in the y direction, which will be F1 sine 85 degrees, and I have F2 in the y direction, which is F2 sine 85 degrees. I also have the force of gravity, which is mg, and that will be negative because it's in the downwards direction. So, F net in the y direction will be F1y plus F2y minus mg, and again motionless, so it's equal to 0. So that will be F1 sine 85 degrees plus F2 sine 85 degrees is equal excuse me, to our mass times the gravity. Well, F1 and F2 are tensional forces. So therefore, 2Ft sine 85 degrees is mass times gravity, telling us that Ft therefore will be mg, so 80 times 9.81 all over sine 2 sine 85 degrees. Which is 383.89 newtons. So the tension in each rope is 390 newtons. And that's one style of question that we might have with a motionless object. Sometimes, however, we might not have that motionless object. We might have, I don't know, let's say a toboggan sliding down a hill, for example. And that combined mass of the children and the toboggan being 100 kilograms. And that hill might also be at an angle of 30 degrees. So we might be asked to figure out what that acceleration would be. So if we have a hill that is at 30 degrees, we might have our toboggan that's now on an inclined plane with a mass of 100 kilograms. In this case, my normal force is perpendicular to the surface, so that's actually Fn. My acceleration in this case is going down the hill. That is the direction of my acceleration in this case. So that allows me to say that up and down the hill is going to be positive. We have our force of gravity acting down. This downward gravity can actually be formed making up two vectors, which are components of our normal force. And from basic geometric properties, we know that this will be 30 degrees right there. That is 30 degrees, that's the number that was just written there. And that tells me that this opposite side, which is going to be our only x component, f at x is going to be right there, which is parallel to the motion of my toboggan. So we know that this is the only force which is causing acceleration down the hill. Mass is 100 kilograms. Acceleration is due to gravity, is 9.81 meters per second squared. If this is the only force that's causing our acceleration, what this tells me is that my net force is equal to F at x, which is mass times acceleration by Newton's second law. What we'll notice, however, is this is a 90-degree angle. So this F at x can be calculated by Fg, because of our hypotenuse being our force of gravity. Sine theta is mass times acceleration, and Fg is mg. Sine theta is my mass and my acceleration. You will notice that both sides of my equal sign here, we have m's, which are common, so they will reduce to 1, they cancel out. So my acceleration is simply g sine theta. So acceleration will be 9.81 sine 30 degrees, 4.905. So the acceleration of the toboggan is 5 meters per second squared. I hope that you are convinced that the only acceleration, the only force is in the x direction, meaning that our y components are going to be exactly the same values. They cancel out. Example 3. Let's save the best for last. Most difficult, which I find these fun. It's like a puzzle that we're trying to solve here. A ball has a mass of 20 kilograms and a block of mass of 50 kilograms, and attached by a lightweight cord that passes over a frictionless pulley which doesn't have much of a mass. Block lies on a frictionless plane at an angle of 30 degrees. We are going to calculate the acceleration of our two objects and the tension in the cord. A systematic diagram, what this looks like, we have mass 1, which is going to be accelerating in the upwards direction towards a pulley, which is at an incline of 30 degrees, attached to a block mass 2. And that mass 2 is going to be accelerating down the incline. When I think about my free body diagram separately, mass 1 merely has the force of gravity and the tensional force, and that will tell us that upwards will be my positive direction for mass 1. Mass 2, which will be accelerating in the diagonal direction, has both a normal force, gravitational force, our tensional force in the other direction, and our y components is made up of F2, which is opposite of our normal force, and that will be in the y direction. And in the x direction, making up our force of gravity will be F2 at x. So we have a heck of a lot of stuff going on in this question. How do we figure out the acceleration and the object? Well, there's a simple way that we must attack this problem. We will attack this problem knowing that it's actually the tension that links both free body diagrams. And we must notice in this case that in mass 1, it's in the y direction, and in mass 2, it's actually in the x direction. But we're going to link those two together, and it's going to be a really elegant proof to figure out our acceleration and our force. So let's now tackle this, knowing that the tension is our link between both. So for mass 1, in the y direction for mass 1, we can determine our net force. That will be tensional force subtract our gravitational force. So that gives me Ft minus m1g is m1a. We will just briefly call that equation 1. For mass 2, it's the tension that links the two together. So my net force in the x direction will be F2x minus my force of tension is mass times acceleration. Now, because this is my theta, which is 30 degrees, that tells me that F2x is Fg sine 30 degrees minus Ft is equal to m2a. Fg is simply mg, so m2g sine 30 degrees minus my force of tension is m2a. And you'll notice I haven't changed my acceleration to acceleration in the y and acceleration in the x. That is because in both directions they are exactly the same. Acceleration upwards is going to be the same because this is a connected series. So, what do I see here? I see in equation 1 that my Ft is positive, and in equation 2 my Ft is negative. And they link together. So we can take equation 1 and actually add equation 2. And let's see what actually happens. This is where the elegant part of math and physics comes in here. That will be Ft minus m1g is m1a. And equation 2, just simply rearranging it a little bit, will be negative Ft plus m2g sine 30 degrees is equal to m2a. These two beautiful guys cancel out. So by adding these two equations now, I have the fact that m2g sine 30 degrees minus m1g is equal to m1 plus m2a. Both these terms had m1 and m2, so I simply just factored them out, because now, dividing both sides by m1 plus m2, I have a mechanism to solve for acceleration. Acceleration, therefore, m2g sine 30 degrees minus m1g all over m1 plus m2. So that shall be 59.81 sine 30. Simple substitution now allows me to solve for acceleration. This will be 49 over 70, which is 0.7 meters per second squared. That's my acceleration in this case. And now it's just a simple matter. Now that I have acceleration, let's go back to equation 1 for 1 second. Ft minus m1g is m1a. Well, to solve for Ft now, I can simply bring my m1g to the other side of the equal sign. So I now have 20 times 0.7 plus 20 times 9.81, which solving gives me 210 newtons for Ft.